Historically, image management relied on eager asset generation. This meant that every time you uploaded a single photograph, your system would immediately resize it into hundreds of pre-calculated static files to match every possible device profile and responsive breakpoint. This creates a massive storage overhead. Enterprise teams end up paying to host millions of media variations that may never actually be requested by a user. Worse, if your design layout changes, you have to spend days or weeks recalculating your entire archive just to update your breakpoints. The modern industry standard has shifted to dynamic, on-the-fly image transformation. Instead of guessing sizes in advance, this design processes and compresses images in real time, directly during transit, delivering optimized assets to the client on demand. Moving to a dynamic, serverless pipeline eliminates storage waste and grants development teams infinite layout flexibility. You no longer need to store variations. You simply define the transformation in the URL and let the system handle the rest. Building this starts with two private Amazon S3 buckets. The source bucket holds your original high-resolution uploads, while the transformed bucket acts as a dedicated storage layer for your optimized outputs. In the settings for the transformed bucket, you must enable a 90-day lifecycle expiration rule for all stored objects. This logic ensures that if an optimized image isn't requested for 3 months, it is automatically purged. This prevents your storage fees from growing indefinitely as your library expands. If a user requests a file that has expired, the pipeline detects the miss and regenerates the asset from the high-resolution source automatically. By treating your transformed images as a temporary self-cleaning cache rather than a permanent archive, you significantly reduce long-term cloud storage costs. The compute phase is handled by an AWS Lambda function. Its job is to parse dimensions from the URL, fetch the original image, apply transformations, and upload the result. However, the specific library you use for this task determines your throughput. Many developers make the mistake of using legacy pixel array processors inside their serverless functions. Legacy libraries decode entire images into memory, creating massive spikes and frequent crashes. The solution is Libvips. Its streaming architecture processes images in tiny tiles instead of the whole file, keeping memory low and performance high. Once the engine completes the resize, the optimized asset is pushed to the transformed S3 bucket to fulfill the request. Pairing a demand-driven engine like Libvips with serverless compute ensures your pipeline can handle sudden traffic spikes without running out of memory. To manage the traffic, we place Amazon CloudFront in front of the stack. This global CDN layer acts as the primary controller for all incoming image requests. CloudFront uses origin failover. For a cache hit, the requested image exists, and S3 serves it instantly. If the dimension is new, S3 returns a 404 error. CloudFront intercepts this, redirecting to the Lambda node, which generates and stores the new image for future hits. This ensures you only pay for compute once per unique image dimension. Once the asset is stored in the bucket, subsequent users are served via low-cost storage and CDN caching. Origin failover is the linchpin of this design, turning an expensive compute process into a passive, cost-effective cache. Leaving a transformation endpoint open to the public web is a significant risk. Without protection, an attacker can exhaust your cloud budget by requesting millions of random, unique image sizes to force constant Lambda execution. You must also account for decompression bombs, maliciously crafted files that expand to consume gigabytes of memory once the processing engine begins to decode them. To defend against this, your Lambda function must enforce strict input and output boundaries. By inspecting image headers and rejecting any file that exceeds your resolution limits, you prevent memory exhaustion. For network-level security, you implement cryptographic URL signing via HMAC. This appends a unique signature string to every image URL, as shown here. Your web application uses a secret key to generate the signature before the page is served to the user. If an attacker tries to manually change the width or height in the URL, the signature will no longer match. The Lambda function will detect this discrepancy and issue a 403 forbidden response immediately. Strict input limits and HMAC validation ensure that your serverless pipeline remains a performance tool rather than a financial liability. By connecting these components, you've built a fully automated request lifecycle. Logic flows from the CDN to the storage layer, invoking compute only when a new asset is required. The operational result is total agility. By changing a single number in the URL path, you can instantly reformat a high-resolution landscape into a tight, optimized square for a mobile thumbnail. Because this architecture relies on standard HTTP 404 interception and reverse proxy behaviors, the configuration is vendor-neutral. You can apply these same patterns to multi-cloud container setups using tools like InProxy, which also utilizes Libvips to provide high-speed, secure transformations. Replacing legacy static pipelines with demand-driven, serverless architectures allows organizations to achieve infinite layout flexibility while minimizing operational overhead and cloud costs.